I want to, again, I want to go back to topology. Right now, I want to make one brief comment about the general setup for finding, talking about what it means for a family, for type of function to be generic, type of singularity to be generic, and so on. First of all, that whole study, goes under the topic of singularity theory, and you're studying different kinds of singularities of smooth maps. You can do the same thing with complex holomorphic maps and so on, algebraic maps, and so that's a huge topic in and of itself, and a lot of what's really sort of founded by Rene Thom, so there's something called Thom's transversality theory, and I'm not going to state it at all, but I'm going to give you the idea. Basically, is that any kind of it's the most general version of the sort of transversality arguments I was trying to make, and it's a very general statement that says if you want what it's about. So we're originally talking about df being transverse to a zero section. Now, df is a section of the cotangent bundle. Suppose you wanted to pay attention. So another way to think about what df is it's it's just a function and its first derivative, right? First derivative. So it's like a first order Taylor polynomial, and then but sort of at each point. So there's this notion of a k-jet of a function. So the k-jet of a function is basically it's just the first k derivatives of a function at a point. Okay, so equals the first k derivatives, and all there's partial derivatives, so there's lots of them. For the first k derivatives at a point. The more fancy way to say it is it's a k-jet. If you have a function on a manifold, a k-jet at a point is an equivalence class of functions, where two functions are equivalent if in some local coordinate system all their derivatives up to order k agree. And so then the k-jets at a point are actually a vector space. And you can think of them as polynomials up to order k, because every function can be, this equivalence class I talked about is represented by a polynomial with those k derivatives, right? So you can think of it as polynomials at a point, which is if you like, you can think of it as the full space of polynomials mod an ideal, where the ideal is all things of order k plus 1 and higher. So you that sort of truncated polynomial. So it's actually an algebra. And you have one at each point in the manifold, so those fit together to be a bundle. And so you get the k-jet bundle over the manifold. And so df is really an example of k-jet bundle over a manifold. And df is really a section of the one-jet bundle. The cotangent bundle is equivalent to the one, but this is a one-jet. And so Thom basically says you can always, there's a very general theorem that sort of says you can make, if you have a function, if you have a function, then right, so given a function, then you get a section of the k-jet bundle. At each point you have its k-jet. So every point in the manifold you get the k-jet, so f gives you a section of the k-jet bundle. And the question is, if you want to make your section transverse to, say, the zero section, or to some other section, or to a particular sub-bundle, all kinds of different things, you're not able to just simply perturb the section, because you don't want to perturb the function. And so the whole question is, can you perturb the function so as to achieve some kind of transversality here? And that's what Thom's transversality theorem says. It basically says, yes, you can just by whatever kind of transversality you want, almost any kind of transversality you want here is a stable and generic property of functions. And then after that, there's if it transversely intersects the zero section of the two-jet bundle or something, then what are the local models for the zero locus and so on. And you also, there's even, it gets fancier and fancier. You can consider k parameter families of functions and their K, L parameter families and their K-jets. You consider S parameter families or T parameter families of functions. There's arbitrarily levels of sophistication, but it all boils down to a transversality argument, and then there's kind of like actually the way you get the local models, pull out those particular polynomial local models is really like ring theory. It's really algebra in theory. You have a polynomial algebra, and you're looking for certain orbits of some action on that algebra, and I won't say more. That's in a nutshell how that all fits into a much more sophisticated theory. Okay, but I want to go back to some topology, and I want to now I want to start telling you about Morse homology. I want to try to motivate this as follows. I want you to remember that if I have P and Q are critical points of the function f, r, x, and their indices differ by 1, index of Q, index of P plus 1, and plus 1, and if all ascending and descending manifolds are transverse, right? Ascending, descending, ascendings and descending are transverse. And if there exists a unique flow line from Q to P, down from Q down to P, then you can cancel. There exists a f sub t with f0 equal to f, and then such that f1 has I'll say which cancels P.
Wait, I don't understand this ascending transverse to descending.
If I say that, just cancels. What I mean is that this is my shorthand for the general property that we talked about, so let me remind you of that. This means that, so this is not really a property of the function, it's a property of a gradient-like vector field. Okay, so it means that we have a gradient-like vector field. Which then gives us ascending and descending manifolds for all critical points. And I could just ask that all possible places where they intersect is transverse, but the only thing I really care about here is that the descending manifold for the higher critical point, I need to talk about this transversality happening in an intermediate level set. Okay? So if I take the descending manifold intersected with f inverse of some value z, so I want some z between f of p and f of q, so some regular value between them. Then I can look at the descending manifold for q inside that level set, so that's going to be a sphere in general, right? And I want that to transversely intersect the ascending manifold for p inside that level set. That's what that transversality means. And that's the condition on, if you think, we're going to be counting dimensions again, so let's review our dimension counts, right? Let's say this is k plus 1, so P has index k, Q has index k plus 1, right? Now the descending manifold for Q, and by this transverse intersection is in f inverse of z. So this is dimension k plus 1. This is the descending manifold for Q. This is the ascending manifold, so it's got complementary dimensions, so it's n minus k. Right? Now we intersect with this codimension 1 level set. So we cut the dimension down, so this gives dimension k. And then this one would also intersect, so this gives dimension n minus k minus 1. And this is all happening inside this level set of dimension n minus 1. And you notice that n minus k minus 1 plus k is n minus k, so their dimensions add up. Right? It's strictly complementary inside this thing. Therefore, transverse intersection we expect to be points. Okay? So, or if you like, codimensions add to the total thing, so therefore they transverse intersection points. And but these are points in this intermediate level set, so each point is really a flow line from one down to the other. Okay? And the reason I emphasize that this cancellation lemma doesn't apply if you don't have that transversality, because you could have kind of two flow lines masquerading as one. Questions? No. So, so now what I want to do is I want to think about, suppose you see in front of you a manifold with a Morse function on it. You see all the flow lines from different critical points amongst each other as ascending and descending manifolds. Can you look at it and decide whether you have a hope of simplifying that Morse function? And this is one way you might try to simplify it. So what I want to do is ask the opposite question: can you see obstructions to simplifying a Morse function? So, what are some obstructions? Cancellation is a way to simplify a Morse function. By simplify, I mean reducing the number of critical points to simplifying a Morse function. And so you could say, well, not having exactly one flow line between two critical points is an obstruction, simplifying. That's not the case, because there may be something else you can do before just canceling. We have other operations we could do. We can handle slides in particular to minimize, to change the number. So the number of flow lines can change, right? So
does that depend on which gradient like vector field you take?
Yes, right. So you can fix the Morse function and start changing the gradient like vector field. So the other thing to remember is it's very useful to think of this intermediate level set in which we see ascending and descending manifolds intersecting. And if I move, let's say I just want to move the descending manifold for a grid point around by an isotopy inside this level set. What we talked about is that isotopy can be thought of, just above it is just a product. So moving it by an isotopy, if I want to move, if I've got a flow line coming down to hit it here and I want it instead to hit it here, if I think of that as a flow line for a vector field, and I want to move this flow line to go over there, all I have to do is tilt the vector field. Instead of doing that, I need to do this, right? So I can modify the vector field only, so that the flow line, the place I end up in this level set, F inverse of t, moves by an ambient isotopy. And any isotopy I can do that because I just basically I spread out the isotopy over an interval. Okay? So we said that's something we mentioned before, that you can always, that's why I can always assume this transversality, because this is much easier than the transversality arguments we were talking about in the existence of Morse functions. And so the point is, ordinary transversality theorem says, submanifolds in this intermediate level set should can be isotoped to intersect transversely, and now we say any isotope in there can be realized by simply modifying the vector field. Okay, so, but the point is there are different ways to achieve transversality, and the relevant events we want to pay attention to are two things. They're handle slides. So what can change? So yeah, the idea is we want to sort of use a number of flow lines from one critical point to another as some obstruction to cancel it. However, if there happen to be three flow lines from Q to P, that doesn't mean you can't cancel, because maybe there's some other way to get rid of them and reduce it to one. Right? So before we try to build this obstruction, let's think about how can the number of flow lines change. So if we just focus on, the answer is there's two things that can happen. We have handle slides, and then I haven't talked much about these yet. I briefly mentioned them before, what I'll call finger moves. And so I think you sort of comfortable with the picture of a handle slide, but let me just give you the picture again actually let me do the finger move first. That's sort of the easiest one to draw a picture of. So if I'm going to give you I'm going to show you how it looks as in a 3 manifold, okay? And I'm going to do it by, rather than drawing the whole embedded thing, which kind of gets messy, I'm just going to draw the images of attaching maps in level set just below it. So suppose I have a 1 handle attached along 2 points. So this is, I'm imagining now, you can interpret this picture 2 ways. You can interpret this, I'm imagining my P, index of P equals 1, and index of Q equals 2 for this example. So here's P interpreted as a 1 handle. And so I could think I'm drawing a picture in the level set below P of the attaching S0 cross D2 for that 1 handle. Or I could think that this is actually a picture of the level set above it, where the understanding is when you come here, you go over and you continue. So in other words, you could say this is also a schematic way to draw what sits above the 1 handle. This is a bit of genus here. I just don't want to draw it. Okay, so anything that enters here goes over genus and continues. And actually, it's really more that point of view that I want to have in mind. But if you have that point of view, the next thing to remember is where is the ascending manifold for this index 1 critical point. Well, it's not in this. It's not in this picture. Here's the 3-dimensional 1 handle, and the ascending manifold is right here. There's a critical point's right there. Okay? Maybe I'll draw. I don't want to draw that there, but I'll temporarily draw it here. So. Here's P. Here's the ascending manifold. And now suppose I have a, let me just do this case, suppose I have a 2 handle that's attached along something. So this is P. And now suppose I have a 2 handle that's attached just along some curve that doesn't even go over P at all. So now there's no critical points. How could I suddenly create more critical points? Well, the reason this is called the finger move now is you stick a little finger out, right? And then you're going to push it up and over. And when it pops out the other side, what has happened? Really, I won't draw the whole thing, but it's gone up and over. Down, and we created 2 critical points where there was only 1. Okay? And in terms of a 1-parameter family of gradient-like vector fields, or a 1-parameter family of descending manifolds, this descending manifold is moved by an isotopy in the, this surface here that I see going all the way over, that's the level set above the critical point of index 1. This thing is just moved by an isotopy, and we suddenly got a pair of intersection points. There was a sort of non-transverse time, that, and then we got a pair of intersection points. So I had 2 intersection points, but if I watch a movie, I see 2 intersection points up together. So I have a 1 manifold worth of intersection points when I go across time. Okay, so that's the finger move, and that was one thing that we discovered when we counted dimensions, that generically you should expect in 1 parameter families, you expect arcs of intersections between index things separated by index 1 as you soup across time, which allows for either have a point that just stays where it is, or you have a pair of points. Okay, so that's the finger move, and then the handle slide. I just remind you also, but I want to what it looks like. But I want to draw a picture like this, and I want you to see how it changes the number of intersection points. Okay, so this created 2 new intersection points from 9, and of course you could do it backwards, and you could have something that goes over. Well, the ending point is you could have something that goes over 3 times, and then but actually really you can undo a finger move, and then it goes over once. Well, maybe just to warm you up also, I could do this whole theory, this whole obstruction theory that we're going to develop over Z2 or over the integers, right? We do it mod 2, and then we just say, well, if there's 2 points of intersection, maybe that's the same as 0, right? We can be more sophisticated. I mean, the 2 becoming 0, right, is either a mod 2 phenomenon, or there's something going on with the signs of these 2 points. And those 2 points should be counted with opposite sign in a certain sense. And if you want to say that what we're going to do, we're going to try to do it properly with signs, right? And which is just a little bit more, slightly more painful, but not too bad. The point is you have to orient everything, right? And so you orient your descending manifold and your ascending manifold. You get orientations of these descending spheres and ascending spheres, and they'll have some orientation. Once you do that, and then you have to make sure you clear your convention for orienting points of intersection between orienting manifolds. Then you get, this would be a plus and this would be a minus, or the other way around. They have opposite sign, and so then they would cancel algebraically in some sense.
Like a Z2 intersection couldn't at all pick up this, right? Because
right.
tell using that.
Right. The point is somehow what we want to take into account when we think of an obstruction is the fact that it's when I see 2 points of intersection, or 2 flow lines from Q down to P, it might be the case that they can be killed, they can cancel each other, right? And so our obstruction theory shouldn't, as soon as it sees 2 points, say, forget it, there's no chance of canceling, right? It should see 2 points and should think, well, maybe they can cancel. Now you can either be really, crude and say, well, if there's 2 points, I'm working over Z2, so it's 0, so great, that allows the possibility of cancellation. Or I'm more sophisticated and say, this cancellation, when it happens, requires them to have opposite signs. And I'm now using cancellation in 2 different ways, right? I'm interested in canceling 2 critical points, but along the way, I want to cancel flow lines between critical points to reduce to the point where I have a single flow line. And that cancellation of critical points is cancellation of flow lines is this. Now, okay, so finger moves somehow add, this, what the finger move does somehow adds or removes pairs of flow lines. And if we're careful about signs, they sort of are added or they come in opposite signs. Then the handle slide, I remind you, we draw a picture of an example of the handle slide again with the same dimensions. What I want though is that, see, a handle slide involves 2 critical points or 2 handles of the same index. But we care about flow lines from index k down to index k plus 1 down to index k. And here's how a handle slide can affect that. Suppose I have a single, let's do, again, I'll do a simple example. Here's a case where I have a 1 handle and a 2 handle going over it at once. Okay, everyone happy with this picture? This means 1 handle like that, and then the 2 handle, this is the convertible roof, right? 2 handle. Now suppose this is my P, and that's not my Q. My Q is somewhere else. My Q is here, let's say. At the moment, there are no flow lines from Q down to P, right? How could there possibly come to be flow lines from Q down to P? If I slide Q over whatever this was, Q0 or something, if I slide that over, then suddenly and suddenly it gets a flow line. So where did it get its flow line from? It got its flow line from the flow line that Q0 had. So the upshot is that when you we'll be a little more careful about this later, but when Q slides over Q0, you get Q picks up a copy of each flow line from Q0. That's the. Now you might say, what if that doesn't seem like it could decrease the number of flow lines, right? Except the two of them together can decrease the number of flow lines. So suppose I've got this, for example, I've got a Q. What could I, as a good example, what can I do next? Let me slide Q0 over Q in reverse. Okay, so let me do a slide right there, for example. And so then what do I get? Q0, I'm going to slide over, so now it goes this way. Okay, do you understand how I get there? I slid Q0 over Q, which means I did a little band connect some of it with a push-off. Remember, I don't have to think about framings because I'm doing the case where n is 3, and so my knots, my attaching circles with the two handles are all in the surface, so the framing is just given to us, right? I'm trying to stay away from the more complicated situation. But now, notice that I can do a finger move here, right? So, what did I do now? Here I had, we can make a little picture of sort of flow lines. Here I had Q, Q0, and P, and I had just a flow line from Q0 down to P. Now I can do, here I have Q, Q0, and P, and I have a flow line from each one down to P. Now it gets even worse, because now I have Q, Q0, and P, and now I have that same flow line from Q down to P, but now I have two flow lines from Q0 down to P. But then I can do a finger move, because I got that guy there, pull it back, I do an inverse finger move, and I get to Q is fine, and then Q0 comes up all by itself. If you care, for whatever reason. Just things that can be done. Great. So well, let me just so here's that's supposed to motivate the following. The claim is those are the only two ways in which you can change the numbers of flow lines between two critical points, because in one parameter families, so now we're thinking of a fixed Morse function, and we're just trying to fiddle around. And in one parameter families of the gradient-like vector field, these are the only things that happen are handle slides and finger moves. The only things that change those flow lines. And the way we knew that was by a transversality argument. And so here's the definition. I want to sort of. So let's define the Morse complex. it's chain complex. If you haven't seen chain complexes, here's your first one. It's not anything really scary or bad. Chain complex means a sequence of abelian groups, a sequence of free abelian groups, and so C dot dot dot, and then some arrows, and then there's going to be CK plus 1, CK minus 1, dot dot dot, all the way down to C0, and actually it starts at Cn. It doesn't go further. We're using the C. So these are each of these is a group. C sub k is a free abelian group generated by critical points in index k. Okay, so that just means it's an algebraic object which is a set of formal linear combinations of critical points of index k with integers, right? So you just take all your critical points of index k, you write some integer next to each one, and that's an element of C sub k. And then I'm going to define what these maps are. These maps are all called del, or boundary map. I mean, really it's to be del sub k plus 1, but I'm not going to make a thing of that. And then, so those are called boundary maps because in some other contexts, they actually are boundaries of things, but here they aren't. They don't count. So now what we need to do to compute them. So to define the generators of the chain groups, I don't need the gradient-like vector field, but to define the boundary maps, I do. So now take gradient-like vector field so that all ascending, I'm just going to say so that ascending and descending manifolds intersect transversely all at once for all of them. Okay, and then let so given a Q, a critical point of index k, define let the boundary of Q. So that's a particular generator for C sub k. The boundary of Q should be a formal linear combination of things in C sub k, a formal linear combination of critical points of index k minus 1. So it's going to be the sum over all critical points P of index k minus 1 of, I'm going to write n sub qp times p. And n sub qp is equal to the number of gradient flow lines from Q down to P. Now you can either take that number mod 2 or you can count that number with sign. So count it with sign, we'll do it that way.
That's just the intersection. Or,
Which is exactly, yeah, so it's the oriented intersection. So really, it's the oriented intersection number of the descending manifold for Q intersected with some intermediate level set. I'm going to put a dot, and I'll tell you, dotted with the ascending manifold P in some level set. And this dot means the A dot B equals the oriented intersection number. So anytime you have two oriented submanifolds and an oriented manifold with complementary dimensions intersecting transversely, the intersecting points and you can assign a sign to each point by saying, take the oriented basis for the tangent space to A at that point, followed by the oriented basis for the tangent space of B at that point, concatenate them, that gives you an oriented basis for the tangent space of the ambient manifold at that point, compare that to the given orientation of the ambient manifold. If they agree, you call it plus. If they disagree, you call it minus. And you should write that down for me. And so that's the oriented intersection number, and that's what I mean by counting the sign. So this is just some math, which is supposed, but the point is it's supposed to count, it's supposed to record for each of these, each generator here, it's supposed to record how many flow lines there are from that generator to all the other different generators here, but it's already built into it is this recognition that two flow lines are maybe just as good as none, right? Especially if they have opposite signs, right? So that's why we're working over the integers and allowing +1 and -1 to cancel. Okay, now it doesn't say, this isn't supposed to be some obstruction. It's not going to be a perfect obstruction. There are many cases where two flow lines don't cancel, but at this level we're not going to see that they don't cancel. Okay. Okay, so what I'm going to work towards showing this is actually a chain complex, which means showing that the composition of two of these operators is 0. But before that, what about, what I want to think about, what do handle slides and finger moves do to this, this complex, this sequence of groups with maps between them? So first of all, finger moves do nothing, right? Finger moves do nothing. They do something to the actual geometry, but they do nothing algebraic because we've already built that in. And that's good because we want something that's sort of robust under these moves. What do handle slides do?
So the thing you finger moves is like changing this vector field?
Yeah, well, these are different. What I want to do now is say, if I change the vector field, how does that change this algebraic structure, right? And so the two things that can happen if I change the vector field are finger moves or handle slides. And then later we're going to talk about canceling, but for the moment don't think about canceling, just finger moves and handle slides. And so I claim that a handle slide is really, you should think of each of these boundary maps as a matrix, okay? I've got some number of generators here, some number of generators here, some number of generators here. And so I've got preferred generators. This is better than a lot of situations where you just have groups where you don't know what the generators are. I know exactly what my generators are. So I have preferred basis, so this is really just z to the power of something, z to the power of something. In those bases, each boundary map is a matrix. And I claim that these handle slides are precisely a change of basis in one of these things, and therefore it affects these in a corresponding way, like add a row. It's like a row operation here and a column operation here or something like that. We'll figure that out a little more carefully in due time, but I claim that they are row and column operations. Elementary row and column operations. Row and column operations. Boundary maps and change the basis. Okay. So let me defer that. I'm going to set up some invariant and show that it's actually invariant. And this is the idea. The idea is we discovered that when you split something over something else, you've got all these new flow lines, right? So if you think of the boundary of Q is really like a column or a row of this matrix, right? And so these numbers here. So you suddenly pick up you've got this column, and then you've got some other column which is the boundary of Q0, right? And so every flow line in Q0 contributed now a new flow line to Q. So that's just adding this column to that column. Another way to think of it is we're just replacing Q by as a basis element, replacing Q by Q plus Q0. That's all. So we're adding one basis to the other. It's actually, I mean, I guess what I didn't illustrate from the picture before is that it also changes flow lines coming from above down to Q as well. But I'll try to say that more carefully.
So the goal is to show that boundary squared equals 0. Boundary squared equals 0 is going to allow us, and so we'll talk about what that means. Boundary squared equals 0 is going to allow us, therefore we can do this nice algebraic thing, taking the homology of this chain complex. And what that means, we're going to define groups called H sub k, and H sub k is going to be, so knowing that boundary of the boundary is 0 means that if I take the kernel of this map, it contains the image of this map. Okay, so the image of this map is if I go from here and then there, I end up at 0. Therefore, the image of this map is contained in the kernel of that map. So therefore, I can take the kernel of the boundary map from CK to CK minus 1 and mod out by the image of the boundary map from CK plus 1 to CK. And this is going to be, for these groups, are independent, they don't change. Although all these boundary maps in these groups can change, these don't change under the Hamel-Slide groups. The algebra to verify that. So if you take this, if you just change your basis here, you don't change. Well, that's sort of obvious. If you believe that Hamel-Slide are really just changing the basis, then this is just abstractly, I mean, as abstract groups, they don't change.
Don't handle slides give you like chain equivalences?
Change in the basis is precisely a chain homotopy equivalence.
But you can't reverse it definitely. No.
Huh? Okay. So I mean, if you don't know what I'm trying to be as elementary as possible with this, right? But that right. So there's a notion of an equivalence amongst chain complexes, and then there's a notion of chain homotopy equivalence and homology, basically the variant of chain complexes up to chain homotopy equivalence. So and then the other thing is what happens. The other thing is what happens if you have a birth or a death in a canceling pair. What does a birth of a canceling pair do? A canceling pair corresponds to a single generator here and a single generator here, and the boundary of this one equals that one. Okay? So birth or death, you have a single generator boundary of Q equals P. That's it. Okay. So what does that mean? That means that, so this Q would be, let's say, in CK plus 1, and this P would be in CK. And if you have this situation, then first of all, you know that Q is not in the kernel, because it's going to something non-zero. So therefore, Q contributes nothing to homology. So Q is 0, it's not C. And then you know that P must be in the kernel because it is in the image. But if it's it's in the kernel, so it does possibly contribute, but it's in the image, so it's 0. So therefore, both P and Q, so there, P and Q contribute nothing to homology. And so the upshot of this is that anything that is non-trivial in homology is something you cannot, any critical points that represent non-trivial homology classes here, that are non-trivial in these groups, cannot be made to disappear by cancellations or Hamel slides and finger moves followed by cancellations.
therefore, non-trivial homology is an obstruction to simplifying your Morse function, to getting rid of critical points. So let's start in on boundary square equals 0, and then after spring break properly, and do the handle slides as row column operations properly. So let me just tell you what the idea is going to be with boundary square equals 0. The other thing to say is that, those of you who've taken algebra, learned algebraic topology the normal way, this seems very different. This is a very different type of generators for your homology. I mean, the algebra is all the same, right? It's a very different kind of class of generators. This is a way of doing homology that's incredibly useful in lots of different contexts, and in particular in floor theory. There are lots of contexts in which you can do the same thing in an infinite dimensional function space. And you want to, let's say, count some special kinds of circles in manifolds satisfying some special property. So you consider the space of all functions of the circle, all functions mapping the circle into a given manifold. And then it's supposed to satisfy some PDE, right? So you want maps of circles in that satisfy some particular PDE. So you consider all maps in, consider the PDE as a functional on that space of functions when it equals 0, or you actually want to take something sort of derivative of that, some gradient function. When it equals 0, that's going to be, you want the objects you're searching for to be critical points of some function. And so they maximize or minimize something. And then you say, okay, to count all of these, I really want to do Morse theory on this large space, including, and I want to find the solutions, which are the ones that are maximized or minimized or are critical points of some functional. And then you do Morse theory on that. And so usually there's some very hard analysis behind all of that. But this is the model for those things. And typically, step 1 is to show boundary square equals 0, which is usually much harder than what I'm going to do, but this is a model. So, what does boundary squared look like? Boundary squared of Q means boundary of Q. Okay? So I'm going to think of Q here. And let's look at the boundary of it. The boundary of it is some sum of critical points. So this is index K. And then there's a bunch of flow lines down. Maybe there's 2 flow lines some places, right? And now, for each of those critical points, I have to take the boundary of it, right? So they go down to some other stuff. Maybe these two added up and sign something, maybe you get something like this. This over there. And now it's going to be, I don't have a good example. Let's see what make it actually work. Okay, if I did this example, then boundary squared would not be 0, right? Because boundary of Q, let's say we're just doing it mod 2, or the sign just worked out, right? The boundary of Q is, well, maybe that's a plus and a minus, so that's already 0. But I've got this, and I've got this, and then boundary of that is, I get these 2 contributions and they cancel, and here these cancel, and then this doesn't cancel. But then we'd like to say maybe there's another flow line there or something, right? The picture is going to be, more or less, we want to show that every flow line that goes from Q, from index K down to index K minus 1, and then continues down to index K minus 2, we want to show that those come in pairs. So for any flow line from, let's say this is Q down to P, this is Q down to P prime, and this is down to R, we want to show for a flow line that goes Q to P and then P to R, there's a corresponding one Q to some other P prime down to some other R. So what you can think of is, what it's going to suggest is that what we want to do now is think about flow lines from index K down to index K minus 2. And here's what we're going to do. We're going to think of each of these flow lines we're thinking of as a point somehow, right? We look at intermediate level sets, and flow lines correspond to points of intersection. So what we want to do is say that the flow lines from index K down to index K minus 2 correspond to intervals of intersection. If I take the ascending manifold for a k minus 2 and the descending manifold for an xk, they're going to generally intersect in one manifolds in some level set. So I'm going to get some one manifold here. And I want to show that that one manifold can be appropriately made compact, one manifold with boundary, and its boundary will correspond to these flow lines that go down like this. So that's going to, the classification of compact one manifolds is going to do it for us. Knowing that every compact one manifold has an even number of boundary components, or if you do sign carefully, pairs them off, then we're going to see exactly this pairing off. So that's what I have to do. Good. Don't forget, I wanted you to write me, you can send my email, you can write on paper, whatever, a list of things, imprecisions that you would like clarified.